Hello, I'm Aditya Chattopadhyay, and today I'll be presenting Gated KalmaNet, a fading memory layer through test time rich regression. As large language and vision models are becoming more and more performant, their ability to process long context length is imperative for unlocking new model capabilities. For example, automating code over large repositories, aggregating information across long videos, or maintaining consistent reasoning traces for agentic applications. For effective long context management, models need some form of memory. In literature, there are predominantly two forms of memory. One is eidetic, that is realized by attention layers, where the idea is we keep the entire past verbatim in memory. This is the KV cache. The downside is high compute. Attention compute scales quadratically with the number of tokens and high storage costs. You have to store all of them in the KV cache. However, attention has almost perfect recall. We can recall any information arbitrarily back in the past. On the other hand, we have fading memory layers like state space models, which compresses the past into a fixed size memory. The advantage now you have low compute, which only scales linearly with the sequence length, and low storage cost. Memory is fixed size, it doesn't depend on the context length. However, most existing SSMs have low recall. There is a significant gap with attention. We hypothesize that the reason behind this gap is that state space models currently are myopic. What do we mean by this? All scalable SSM layers in practice today share a common linear recurrence. Here, ST is the state at time t, which is our compressed memory of the past. AT is a transition operator, which controls what to forget from the previous state. VT is the input at time t, and BT is the gating operator, which controls how the incoming token should be written to the memory. So here's the catch. At every step, what to forget and what to write are functions of only the current token. And that is why we argue that these models have low recall capabilities. Because ideally, you want to also look at the past to decide, what to forget and what to write. Contrast this with the RNNs and LSTMs from the 90s. There, this transition and gating operator was actually a nonlinear function of the previous hidden state and the current input. However, this design was not scalable. Our contribution, Gated KalmaNet, to the best of our knowledge, is the first non myopic SSM at scale. What do we mean by this? Gated KalmaNet updates its state using the entire past. So here, both AT and BT depend on this factor G, which is a nonlinear function of all the keys seen so far, thus the entire past, not just the current key. Next, we achieve this while still enjoying the linear time compute and constant storage benefits of SSM. And our model scales due to efficient Triton kernels. We have validated Giga up to 32 billion parameters. Giga has comparable runtime with existing SSMs. In this plot, the green curve, Giga, you can see is faster than the purple curve, attention, as the sequence length increases. This is because our compute complexity is linear, whereas attention is quadratic. Interestingly, even though does much more computation than gated DeltaNet, a popular SSM, the speed is comparable, and this is because of our efficient Triton implementation. So, does this help? Using the entire past to decide what to forget and what to write. We test Geek on language modeling tasks across several different prototypical tasks from LM harness. We see gated KalmaNet outperforms other SSMs like Mamba 2, gated DeltaNet, gated linear attention, so on. And interestingly, if you look at the recall oriented tasks, FDA and SWD, which requires finding specific information from the past, Geeka is the strongest SSM. Next, we test Kika for hybrid models, which mixes attention and SSM layers to get SSM's efficiency with attention superior recall. We train hybrid models at 8p scale and find that hybrid Giga has the strongest long context capabilities across many different long context tasks. Beyond language, we also evaluate Giga on image classification tasks. In particular, we take Mamba Vision, a state of the art hybrid model that employs SSMs, and replace the Mamba layer with Giga. We find that without any vision specific changes whatsoever, Giga outperforms Mamba and is still faster than a transformer VIT model. If you're interested to know more about our work, please come visit us at our poster session. Thank you.